Look up at the night sky. In our cosmic neighborhood, we find overwhelming silence. Physics dictates the formation of stars and planets, but biology demands something far stranger: self-awareness. If the universe seeks complexity, why is developed intelligence so demonstrably rare? For decades, we treated intelligence as an inevitable evolutionary destination, a steady climb up a ladder. But investigative science now shows us a different, far more perilous path. Intelligence is not destiny. It is a precarious, expensive, and profoundly unlikely series of evolutionary bottlenecks. This is the true story of how life hacked the code of the universe. We will track the three monumental prerequisites: embodiment, sociality, and abstraction, and analyze why failure at any single point could have rendered our planet mute. This journey redefines what it means to be conscious and why that consciousness matters. The first great leap is embodiment. Before brains could calculate, they had to move. Intelligence is fundamentally about prediction, not just reaction. But prediction requires centralization. How do you decide what needs predicting? The bottleneck arrived 540 million years ago with the Cambrian explosion. The emergence of bilateral symmetry, the simple concept of having a front, was a game-changer. Suddenly, organisms needed a central hub to process incoming stimuli, propelling the first true nervous systems. But a central brain is only as good as the information it receives. The cognitive architecture of an octopus or a human is intimately linked to its peripheral body. Our gut, our skin, our hands, they are not just appendages, but essential computational arrays that feed the core processor. This leads to the crucial feedback loop. Movement demanded better prediction, which demanded better centralization, which enabled more complex movement. If life had remained sessile or simply radial, like a sea anemone, the vast metabolic cost of a centralized brain would never have been justified. It was the movement imperative that secured the initial investment. The second critical bottleneck is sociality. Large brains are incredibly expensive, consuming 20% of human energy despite making up only 2% of our body mass. To justify this cost, intelligence must deliver an astronomical return on investment, and that return, for primates, was found in cooperation and conflict. Our ancestors' move into complex arboreal and then terrestrial environments placed immense pressure on spatial reasoning and collective hunting. But the real cognitive leap was mastering the intricacies of a group. Who is trustworthy, who is dominant, and who is allied against whom. Intelligence became a weapon for social maneuvering. The demands of group living required the development of theory of mind, the ability to not only observe behavior, but to infer intentions, beliefs, and emotions in others. This is the cornerstone of consciousness as we know it. Robin Dunbar's research quantified this pressure, suggesting a limit to stable social groups, the famous Dunbar's number. To manage larger groups and maintain complex relationships, simple emotional cues were insufficient. We needed abstraction, symbolic language. This social pressure cooker accelerated brain growth far past the threshold needed merely for survival. It wasn't environmental threat that made us smart. It was each other. The competitive and cooperative complexity of human relationships paid the metabolic bills. Finally, we crossed the threshold into abstraction. Even with large, socially tuned brains, a fundamental physical limitation remained: calorie restriction. Our ancestors had massive digestive tracts, competing fiercely with the brain for vital energy. The discovery and mastery of fire was the ultimate metabolic cheat code. Cooking predigests food, effectively externalizing part of the digestive process. This biological windfall freed up massive caloric resources, enabling the rapid and sustainable expansion of the cerebral cortex. The physical hand-brain synergy was next. As tool use advanced, the motor planning regions of the brain became exquisitely complex. But true abstraction occurred when we realized we could use a concept, not just a tool, to solve a future problem. That is the birth of engineering and philosophy. This ability to simulate the future and model hypothetical realities is arguably what we call consciousness. We evolved to run complex internal simulations based on collective data. This computational power provided the critical edge in a world demanding long-term planning and contingency measures. But the final and most crucial hack was external storage. The invention of writing and later digital infrastructure allowed us to offload the cognitive burden of memory and computation into durable collective systems. We stopped relying solely on genetics and individual memory. Culture became our ultimate, rapidly upgradable intelligence system. If we analyze the path, intelligence is not the result of general evolutionary pressure. It is a fragile tower built on lucky geological circumstances, metabolic surpluses, and profoundly unique social pressures. Remove bilateral symmetry, fire, or the necessity for social cohesion, and the cognitive leap fails. This analysis provides a stark context for the fermiparadox. The silence of the universe might not be due to self-destruction, but simply because the evolutionary prerequisites for complex, communicating intelligence are statistically astronomical. We are not just special, we are wildly anomalous. Understanding intelligence as a series of hacks, rather than an inevitability, shifts our perspective. It moves the conversation from, what is the ultimate fate of intelligence, to, how do we responsibly manage this profound, cosmic lottery win? The evolution of intelligence is complete. Now, the era of managing its consequences begins. Let us know in the comments. What do you think is the next great evolutionary hurdle for human intelligence?